doing some inverse trigonometry. And you should think of inverse trigonometry as being a lot like the stuff that we did when we defined logs. We had some function called exponentials, which we were interested in because they model things like population growth and stuff. As soon as you want to solve a problem that involves exponentials, you need a way to undo exponentials. That's the job of log functions. Well, we have a reason to be interested in trig functions. Anything that has to do with triangles or angles or locations that come from circles, those involve trigonometry. If you want to solve equations that come from that, you need to undo trigonometry. Let's undo trigonometry. So here's the basic idea. So here is a right triangle. Its hypotenuse is length 8. It has opposite side length 1. Let's suppose you wanted to know what on earth is that angle theta. You could say some things. It looks like it's a positive angle. It's certainly less than 90 degrees because it's an angle in a triangle. In fact, it looks like it's less than like 45 degrees. So what will we do here? We'll make up a name for it. So let's just describe it. So this is the angle in quadrant 1 with sine of theta equal to 8. Right, quadrant 1 corresponds to acute angles. Angles less than 90 degrees. We'll give this angle a name. In fact, we'll give it several names. Oh, sine equals 1 over 8. Yeah, when I write something that's obviously stupid.
Well, I was trying to make sure that it was not me.
Okay.
I double checked.
Yeah, I'm the one who was done there. Sine can never be 8. That is way too big for sine. Sine is at most 1. So we'll call that inverse sine of 1 over 8, or arc sine of 1 over 8, or depending on what particular machine you're using, you might enter it as a sine 1 over 8. And now that we have a name for it, we can ask a computer for an approximation. So this angle is sine inverse of 1 over 8. I'll invite you to, if you have one and you want to, pull out a machine right now. Pull out a little handheld calculator. See if you see something that looks like an arc sine or a sine or sine inverse button, and get an approximation. While you do that, I'll do the same. A sine of 1 over 8. Parentheses probably matter here. I see around 0.1213, 0.13 radians. Does that agree with what other people are getting? Is anyone getting a number that looks a little bit bigger because you're in degree mode? I mean, I assume. But what is this in degrees? 7.2. About 7.2 degrees. Oh, so now maybe I'll ask you this question. Do you think this picture is drawn to scale? No, that length of 8 is obviously not 8 times as long as the length of 1. That angle also looks like it's much bigger than 7 degrees. Groovy. We feel pretty good. So that's the idea of inverse trigonometry. We want to find those angles, and we have a name for a function that computes them. I'm not going to disclose much about how these approximations are done. The calculator is going, well, you know what I'm going to say. Like I've said it a few times. The calculator is doing some secret magic stuff that comes from Calculus 2 involving Taylor series. We won't talk about those, but there are some obvious things we can do, and we'll do some of them. So motivation. So in order to solve exponentials, we needed inverses. So just like 3 to the x equals 5 has solution log base 3 of 5, the solutions to trig equations are inverse. They have to do with inverse trig functions. That seem pretty okay? So let's start with this. So I guess this is exactly the question we just answered. That you see two graphs on the board. One of them is sine, one of them is cosine. Which one's sine, which one's cosine? I heard cosine, but not which one. I like that. I guess this one must be sine. And remember, I want to think about inverse functions to these functions. Are those one-to-one functions? So think about the horizontal line test. Do they pass it? Not the vertical line test. That's one that says if they're functions. Horizontal line test says, how many times does this horizontal line cross? Is it more than one? In fact, is it infinity? If I kept going, right? I only see 4 right now. And same thing with cosine. So these are very non-one-to-one functions. In fact, they're like infinity to one functions. So that's really bad from the point of view of inverting. If you flip those over the line y equals x, you get a really tall squiggle. That fails the vertical line test. That's not a function. These don't have inverse functions. So why aren't we studying inverse functions to these things if they don't have inverse functions? Well, there's already one case that you've done that. If I ask you, what's the inverse of squaring, what would you tell me? Square root. But does squaring actually have an inverse function? No. It fails the horizontal line test. So what do? You think about restricting the domain. If you take x squared and just restrict it, so no, it doesn't. If you restrict x squared to just positive numbers, is that one-to-one? Yeah, now it passes the horizontal line test, so it has an inverse function. And, I mean, you know how to graph the inverse function. It's split the role of x and y. There it is. You already have a name for that orange function right now, don't you? That's the square root. So if you have a function that you'd like to invert, but you can't because it fails the vertical line test, it fails the horizontal line test, just think about how much of the function you could use without failing the horizontal line test, and go from there. So let's go up to the graphs of sine and cosine above. So I'll start at 0 on both of them and start by going a little bit to the right. So let's start with sine. Starting at 0, how far to the right can I go before I fail the horizontal line test? Yeah.
Up to the peak of that.
Yeah, up to the turning point, I guess, is the technical word. And where is that turning point? Pi over 2. Excellent. So I can go up to pi over 2. How far to the left can I go? Yeah, negative pi over 2. So if you only saw the blue part of this function, only that bit that I've just highlighted, you only saw that much, would you say that is a one-to-one function? Yeah, that's the function we'll try to invert. Do the same for cosine. If you start at 0, I guess 0, 1, and start going to the right, it looks like eventually you'll stop being one-to-one. You can't go past the turning point. In fact, do you think in general you won't go past turning points whenever you want to do this stuff? Yeah. Where is that turning point? Pi. And I guess the x-coordinate is the most important thing for us right now. Maybe I'll record the y-coordinate too, because otherwise I'd wonder why am I labeling it as a point. If I only see that much of that function, it's one-to-one. That's the function that I'll invert. So what are the inverse trig functions? Well, here are the trig functions with their domains restricted. So here's the graph of sine of x. Here's the graph of cosine of x. Here I've restricted the domain to be negative pi over 2 to pi over 2. And I see the range is negative 1 to 1. So I've only drawn a piece of sine. I've drawn sine only from x equal negative pi over 2 to pi over 2. That's a perfectly reasonable way to describe a function. It now has smaller domain. here's the restriction of cosine. What if I restricted the domain to be here? 0 to pi. And what's the range? Same, -1 to 1. So that's nice. So I've restricted the domain, but the range is the same. That's something anyway. The range being the same is kind of important. On those domains, are sine and cosine 1 to 1? Yep. So they have inverse functions. So I am now ready to formally write down the definition of inverse sine, also called arc sine, also called a sine. Ooh, so on your handheld calculators, those of you who brought it out to do that computation earlier, sine raised to the -1, what was it called that on your calculator?
The bottom ones, but then we're going to put it here in the screen.
Cool. That's interesting.
I use my phone, but that's probably why.
Maybe. It's interesting that the button didn't line up with what it showed on the screen. Yeah, so depending on your calculator, you'll see one of those three, possibly multiple of those symbols. A sine, arc sine, or sine inverse. So sine inverse is the inverse to sine once you restrict the domain, and maybe I'll be specific, sine's domain restricted to -π/2 to π/2. Inverse cosine, also called arc cosine, is the inverse to cosine with cosine's domain restricted to 0, pi. Right, in reading, it's really ambiguous what that it refers to. So I want to be explicit. So let's write down let's rephrase this. So that means sine inverse of y is the angle between these two numbers, -π/2 and π/2, which satisfies that sine equals this number. So when you say sine inverse of y, you're saying I want an angle which has that as the sine. That makes sense. And that angle has to be the one between -π/2 and π/2. So in this range. Inverse cosine, that's a typo, is the angle between 0 and pi. And let's call it x, because cosine should be the x coordinate. Inverse cosine of x is the angle between 0 and pi with cosine equal to x. So there, x is the same as that x. So when I say inverse cosine of a number, I'm saying I want the angle which has that cosine. That angle has to be between 0 and pi. So quadrant 1 or quadrant 2. Feel pretty okay? So I'm belaboring these definitions because some things can get subtle unless you remember exactly what these things mean. So let's read off some things. So what is the domain of inverse sine? What are the numbers you can possibly plug into it? -1 to 1. I guess there are a few ways to see it. What's the range of this function? -1 to 1. So the domain of the inverse should be the range of the original. So it should be -1 to 1. But it also needs to be a number that can actually be hit by sine. And what outputs does sine ever take? What's the biggest sine can be? What's the smallest? So that'll be between -1 and 1. What's the range of inverse sine? -π/2 to π/2. Inclusive or exclusive? I hear an inclusive. So let's think about this the same way. What's the range? Well, no, I want the range of the inverse sine, so I want the domain of this function. What's the domain of this function? Well, it's like written, right? It's -π/2 to π/2. Well, the range of the inverse function is the same as the domain of the original. So yeah, it should be that. And notice, inverse sine of y is an angle that is between -π/2 and π/2. So the range is what things it sits between. Same thing for cosine. What's the domain of inverse cosine? -1, 1 by the same reasons. What's the range of inverse cosine? 0 to pi. Did you think about that by thinking about the graph or by this notion down here? Yeah, I guess that's the easiest. Yeah. Cool. So we have these descriptions of the inverse trig functions. Do you think we could also get their graphs by thinking about what inverse functions do? How do you get the graph of an inverse function from the graph of a function? Yeah. Flip it over y equals x, which has the property that it changes x values to y values, and conversely. So let's do that to this. So here's the graph of sine. So let's use that to sketch the graph of sine inverse. So I see here the point -pi/2, -1. So where will that point go when you do this transformation? -1, -2. Oh, looks like I even labeled it. Is it the other point that should be on there? Nice. It also looks like the point 0, 0 is on the graph of sine. So where will that point go? 0, 0. Cool. And now I guess we can just draw this picture but turned on its side. So instead of being super horizontal right there, it'll be basically vertical, come through and pass through the origin, and then become basically vertical again. Does that feel pretty okay? Cool. Let's do the same thing for cosine. Cosine goes through 0, 1. So inverse cosine will go through 1, 0. Cosine goes through pi/2, 0. Inverse cosine will go through 0, pi/2. Cosine goes through pi -1. Inverse cosine will go through -1, pi, basically vertical there, goes through this y-axis, and then becomes basically vertical again at the other end. That idea seem reasonable? Yeah. And I guess these are weird-looking graphs, right? It looks like they should continue on. They don't have a vertical asymptote or anything. They just stop because that's where they stop. That's where our definition breaks. People feel pretty okay? Nice. So let's use this to do some things. Let's start by making some computations. Let's try to compute sine inverse of -1/2. So to do that, I need to find an angle whose sine is -1/2, and which sits between -pi/2 and pi/2. By looking at your unit circle, can you see such an angle? Yeah. I hear a pi/6. And let's just go ahead and check that it satisfies these conditions. I hear -pi/6. It has been revised. Is the sine of -pi/6 equal to -1/2? And people would need to stare at the unit circle for a second to see that. Yeah, I mean, you have the unit circle in the other notepad, though, right? So pull that out if you need it. Check that fact. Maybe I'll pull it out on my end as well. Yes, there it is. So -pi/6 means rotate backwards by pi/6. Yeah, that y value is -1/2. Cool. Is -pi/6 between -pi/2 and pi/2? Yeah, good. I think it works then. People feel pretty good? How many people would have been tempted initially to say 11pi/6 for this answer? Okay. I mean, if you rely on this too exclusively, you would say, 11pi/6 has sine equal to -1/2. What's wrong with 11pi/6, though? Yeah.
It's not within -pi/2.
It's not between -pi/2 to pi/2. So, I mean, I guess you just have to add a 2 pi to get it between those two. So if you come up with an initial guess that's not acceptable, just add some pi/2s. Or subtract some pi's over 2. All right, let's do some more. Cosine of negative root 3. Let's make that over 2 so it's something that's actually on the unit circle. Same thing with sine. Compute for me the inverse cosine of negative root 3 over 2. And maybe I'll go ahead and put this thing there if you need it. Of course, the more I use this, the messier it'll get. So here's the thing to think about. By looking at this unit circle, do you see an angle where cosine is negative root 3 over 2? What angle do you see? Excellent. I got both answers. 5 pi over 6 and 7 pi over 6. So let's write them both down for now. 5 pi over 6 versus 7 pi over 6. Can't be both, right? The function can't take two different values. And so you're experiencing here the exact same thing that makes why when you see a square root, you often see a plus or minus next to it. There are the two choices that you should have for when cosine is equal to negative root 3 over 2. What's the range of inverse cosine? 0 to pi. So let's write that down. So the range is 0 to pi. So that means if this is actually a function, only one of those two can be between 0 and pi. Which one's between 0 and pi? 5 pi over 6 is. So there are the things to think about. So find yourself the angles that have the right cosine. There's step 1. Step 2, which ones actually live between 0 and pi for inverse cosine, negative pi over 2 to pi over 2 for inverse sine? People like this idea? Next question. Sine inverse of negative root 3 over 2. So I'll go ahead and flash this back up. So, do you see an angle or some angles where sine is equal to negative root 3 over 2? Say louder. I hear a 2 pi over 3. I hear a negative 2 pi over 3. Do I hear any other angles that have that sign? Yeah.
Isn't it just negative pi over 3?
I also hear a negative pi over 3. Well, let's check. So negative 2 pi over 3, let's see, there's negative 1 pi over 3, there's negative 2 pi over 3. Also has the right sign.
Oh.
But this one also has the right sign. And this is the same issue. There are multiple angles that give you the same y value. In fact, maybe I'll write more. So also is 5 pi over 3 and 4 pi over 3, right? Like those are the ones you literally see on this particular unit circle. All right, so there are a bunch. Let's ask ourselves, of these angles, which ones are between negative pi over 2 and pi over 2? I guess ideally only one is. Is this between negative pi over 2 and pi over 2? No, 2/3 is bigger than a half, so that's no good. Is this one between negative pi over 2 and pi over 2? And let's just make sure that it's actually a function by ruling out the rest. Is this between negative pi over 2 and pi over 2? No, it's like almost 2 pi. How about this one? Nope, it's bigger than pi. So negative pi over 3 looks like the right one. Nice. Folks feel pretty good? Cool. So we have these doodads, and I really want to come back to why you should care about these doodads that are inverse trig functions. They let you solve problems that involve triangles. If you have information that requires you to figure out what an angle is and you know some sides, you need to do inverse trigonometry. So here's one such example. Here is a right triangle. Let's use inverse trigonometry to compute the angles alpha and beta. And I'm calling for approximations in radians and degrees, so let's try to find them. So let's think about this angle alpha. So without telling me alpha, what trig function of alpha do you already know? Using SOHCAHTOA, right? You know cosine. What is cosine of this angle? Is 4/5. Maybe just to be contrarian, I'll write it as 0.8. Oh, nice. So cosine of alpha is 0.8. Is alpha between 0 and pi radians? Yeah, it's an angle in a triangle. It's between 0 and pi/2. Oh, neat. That means alpha is inverse cosine of 0.8. And that's now an exact value. If you want to know how big it is really, I guess that means I need a decimal approximation. What is that about? In degrees or radians? (6.1). Thank you. Cool. That seemed pretty all right. Let's also find beta. Did people get differing answers from that? Excellent. Let's figure out beta. How would you figure out beta? You know the sign. So here's one philosophy. What is the sign of beta? Yeah, also 0.8. So does that mean beta has to be sine inverse of 0.8? Oh, cool. So we can figure that out. What's inverse sine of 0.8? What do we get? 0.93 radians. I'm just doing that so I'm consistent with the number of digits above. In degrees? Cool. Let's also notice one more thing. What do the angles inside of a triangle have to add up to? 180 degrees. And this is a right triangle, so what do alpha and beta have to add up to? 90 degrees or pi/2 radians. Let's just use that to make a quick check that this is correct. Add those two things together. Is that about 90 degrees? That's good. I guess it's harder to tell if you add up the other two whether that's about pi/2 radians, but hopefully it is. Nice. In fact, did we need to compute beta using inverse trigonometry at all? How many people would have had the instinct to just subtract from 90 degrees? Yeah, that's a reasonable instinct to have. Nice. So, if you know things about a triangle, you can use that information to find angles. So if you want to solve a triangle, you say, no, 2 side lengths and an angle. Do you think that's enough information to find all of the sides and all the angles of that triangle? Yeah. So I think we won't, just in the interest of time, because I think that first example went so very well. Let's now think about something else you can do with inverse trig functions. Let's think about compositions like this, cosine of inverse cosine. And let's compute this from the inside out. We'll notice a pattern pretty quickly. What's inverse cosine of 1/2? Possibly by looking at your units also. pi over 3. So cosine of inverse cosine of 1/2 is cosine of pi over 3. Oh, but now also look at your unit circle. What's the cosine of pi over 3? 1/2. Oh, neat. So do you think should just like always happen? Let's do at least one more check. Let's do it at 1. Let's compute sine of sine inverse of negative 1. Negative 1. What's sine inverse of negative 1 by looking at your unit circle? Negative pi over 2. Oh, did you say something other than that? Okay, excellent. Good. And now, by looking at your unit circle again, what's the sine of negative pi over 2? Negative 1. So, here's the thing that maybe you're noticing. When you figure out the thing that goes inside of those parentheses, you're just looking for an angle that has that sign. So, of course, the sign of that angle is that number. You chose it to be that. So it sure seems like the cosine of the inverse cosine should always be the input. The sine of the inverse sine should always be that input. But there's one subtlety. Let's try to compute cosine of the inverse cosine of 12. What's the inverse cosine of 12? It doesn't exist. What's the cosine of something that does not exist? Yeah. So trig of inverse trig is always equal to the original input as long as you're inside of negative 1 to 1. Let's think the other way. What do you think that cosine inverse of cosine of x should probably be? If you were to just make a guess what should go there, it sure seems like it should be x, right? I'll put a question mark there just to indicate that I'm not so sure. Let's try to compute it. Let's compute the inverse cosine of the cosine of 3 pi. So first things first, what's the cosine of 3 pi? Negative 1. Right, it's 1 pi, 2 pi, 3 pi, negative 1. What's the inverse cosine of negative 1? It's pi. Right, so look at the unit circle. Do you see an angle where cosine is negative 1? Yeah, it's pi. And pi is between 0 and pi because it was inclusive. Oh, so is the cosine of the inverse cosine of x always equal to x? No, it looks like some stuff can go bad. And just like how the square root of x squared isn't always x, it's the absolute value of x. Like, you're not losing plus or minus information, you're losing something else. So they don't quite cancel. In fact, oh, Chris, what am I doing? I just want to go to the next page. In fact, we can get the graphs in general, but let's try to do one more computation. Let's try to compute inverse sine of the sine of 5 pi over 3. So, following the same pattern, what's the sine of 5 pi over 3? Negative root 3 over 2. What's the inverse sine of negative root 3 over 2? I had a negative pi over 3, and let's just do that sanity check. So it needs to be between negative pi over 2 and pi over 2. There's negative pi over 2 to pi over 2. It looks like here's the point I'm looking for. This points to 5 pi over 3, but that's too big. You want to think about rotating down to it. You rotate down negative pi over 3 to do that. So yeah, negative pi over 3. So again, it's not the same as you wanted it to be. And yeah.
So like if you just, before you did any of the sign calculations, the inverse sign, you just simplified 5 pi over 3 to, or you just like found the one that's in, if you found it, yeah, you know, you found it in the domain first, then you can arrange it.
Yep. So that is exactly the content that will happen like starting here. That is and more so right here. If you want to compute inverse sine of the sine of an angle, you just want to figure out, well, if you take that angle and do some stuff to it while preserving sine or preserving cosine, how can you get it in the right range? And what's the resulting angle? And I think it's also neat to just see the graphs of the thing. So there's a computer-generated graph of the sine of inverse sine of sine and inverse cosine of cosine. Maybe I'm not telling you which. Let's do a quick thing to check which. Which do you think is which? I hear a call for the left one is inverse sine of the sine of x. Why? Okay, it looks vaguely siney. That's not an unreasonable intuition to have. Maybe I'll test by plugging in a number. It looks like they have different behaviors at pi, right? Right here, it looks like it's. Oh no, the x-axis is mislabeled. No, it's labeled correctly. So it looks like up here it's pi comma pi. That point is pi comma 0. Let's try plugging pi into this. So sine inverse of sine of pi. What's the sine of pi? What's the inverse sine of 0? What's the best angle that has sine equal to 0? 0. So that checks out. I guess this one must then be inverse cosine of the cosine of x. That feel pretty okay? And those are just neat sawtooth graphs to know what they are. Groovy. So, I think maybe I'll hold off on this. Let's jump down to these examples because I think these will hit the thing that you just said really well. So let's suppose you want to compute the inverse sine of the sine of pi over 5. 25 plus pi over 5. And I'll follow these exact steps. So the first thing to think about is I'm evaluating sine. Well, follow these steps as is. So let's figure out what quadrant that lives in. And let's throw out any excess 2 pi's. Are there any excess 2 pi's in that angle? Yeah, 12 of them, I guess. So let's replace that 25 pi to just pi plus pi over 12. Sine inverse of sine of pi plus pi over 5. What quadrant does pi plus pi over 5 live in? Quadrant 3. Well, now remember, the range of inverse sine is negative pi over 2 to pi over 2. That's this range. Does that range include quadrant 3? No. So here's the angle that we actually have in this example. What would you do to change that angle to be something that is in quadrant 3 without changing sine? What would you reflect it over? You would reflect it over the y-axis. So let's reflect over the y-axis. So if you are in a forbidden quadrant, so that's, I guess, quadrant 2 or quadrant 3 for sine, then reflect over the y-axis. What does this angle become when you reflect it over the y-axis? I hear a negative pi over 5. Did you do that geometrically or algebraically? Did you subtract, I guess? Yeah. So I guess that pi over 5 became that pi over 5? Yeah, reference angle is the one. Equals sine inverse of sine of pi over 5. All right, step 3, add or subtract some 2 pi's if you're not already in between negative pi over 2 and pi over 2. Is that angle between negative pi over 2 and pi over 2? Yeah. It is negative pi over 5. What are you talking about? Yeah, same question though. Is it between? Is this angle between negative pi over 2 and pi over 2? It is. So we're done. This is negative pi over 5. Let's try to do the same thing for cosine. I think we have time to. Yeah. I think this is good. So let's try to do cosine. Let's compute the inverse cosine of the cosine of 25 pi minus pi over 5. It becomes a different question if that cosine is a sine. It's not much harder, but there's one more bit of subtlety that I don't want to deal with. Right, sine is just a shift of cosine, so it's not that much harder. Let's try to do that. So step 1, are there any excess 2 pi's we could throw out? 12 of them. So this is the same as cosine inverse of the cosine of pi plus pi over 5. And same question, what quadrant is that in? Yeah. That one? It does. So, what quadrant is that in? Quadrant 2. And let's remember, the range of inverse cosine is 0 to pi. Oh, I want to color code this. There's 0 to pi. Is this angle in that range? God damn it. All right. Okay. Thank you. That would have been quite embarrassing. Because is that angle in the desired range? So we don't need to do any reflection. If it weren't, then what reflection would we need to do? We'd reflect over the x-axis. So if your angle is in a forbidden quadrant, so that's quadrant 2 or quadrant 3 for sine, quadrant 3 or quadrant 4 for cosine, then you'd reflect over the x-axis. Okay. Now ask yourself, well, this number is like 4 pi over 5, right? Cosine inverse cosine 4 pi over 5. Is that number 4 pi over 5 between 0 and pi? Yeah. So what's the inverse cosine of the cosine of this thing? 4 pi over 5? So whenever you want to compute sine of inverse sine of a thing, or inverse sine of the sine of a thing, or inverse cosine of cosine of a thing, here are the steps to do. First, decide what quadrant your thing is and draw out any excess 2 pi's. If you're in a forbidden quadrant, then do a reflection. And if you need to think about like what algebraically does that reflection, well, maybe we'll write it down. So to reflect over the x-axis, I guess that replaces an angle by negative that angle, right? Or 2 pi minus that angle if you prefer. To reflect over the y-axis, that replaces an angle by pi minus that angle. So there are the things to think about. So what shows up on the next page? On the next page is 4 more computations of the exact same type. 4 more examples of computing trig function inverse of trig function of a number. So, over the course of the weekend, take a look at these 4 examples. Decide if you want to see examples of that form worked out. If there is demand, then we will do it. I suppose if there's demand to see it done right now, I'm not going anywhere. As the other class trickles in, if you want me to do it, I can do it. Anyone want to see one of them done instead of leaving? That's fair. Have a good weekend if I don't see you during my office hour.